Okay, in this lesson, we're going to talk about concavity. As I said to you before with these graphs of polynomials, one of the major things that we need to consider is the fact that there are times where this graph, it might have these intercepts, but there are other things going on in between those points. You might have points of horizontal tangency, but there could be points of which is literally doesn't have a slope because it's a vertical drop. Or it could be that there's some jagged edge. There could be other things that are going on in between these significant or critical points. That being said, when we're looking at the concavity, it tells us so much, and we should be able to determine its concavity without even drawing the graph. And that's kind of what we're looking at today. Yes, we'll be working on drawing graphs and sketching those curves, but really what I want to get you to is so that you don't have to actually draw the graph. What tells us about whether this graph is opening up or opening down? I want you to think with me for a minute in driving a car. Picture for a moment that you're driving on a winding road. And as you're driving on the winding road, you go from right and you go around a curve, and then you come to the left and then you go around a curve. And if, for those of you who are local and maybe have been to the Enchanted Forest, there's a road that you travel on called the Moose River Road. It's probably the best picture of what I'm talking about. That you literally are doing like these zigzags around basically along the river, Moose River. And so it's literally going from right to left to right to left. Now, if you think about it, there are the points where you're at the maximum and then you flip to the left. At some point, if you could picture your steering wheel and your wheels, you've got your wheel turned to the right as you turn to the right, and then you turn it to the left. But at some moment in time, your wheels are straight. And that point on that curve, the point at which your wheels are perfectly straight, you're not turning to the left or to the right, it's that moment of transition between those two, is what we call the point of inflection. And we're going to get into that. But since I'm describing this to you, I want you to just kind of look. I'm going to kind of talk you through this video here. You have here this car, so just picture the winding road. And as they turn from the right into the left, so they're coming around the curve, at some moment, boom, it's going straight. And then it starts to turn again as it's going down the next winding path. Just had a little fun in there. Sorry. But that point of inflection, hopefully, was clear, even though I was kind of messing with you a little bit. Okay, concavity. Decreasing slope, increasing slope, all of those things I want you to consider. As we see a curve, it will have decreasing, and then it will have increasing shortly thereafter. Overall, the slope, though, the slope is increasing because these are all negative, 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 and then it gets more positive. So I want you to think, okay, so this would be -5 and maybe -2 and -1, and then you have -1/2, and then you have 0, and then you go to +1/2. If I was to number that on a number line, you could agree that overall the slope is increasing and becoming more positive. That's the key about that. And when we look at the concavity, that's what I want you to pay attention to. What we use in this case is our second derivative. Now, what is the second derivative? The second derivative is basically the derivative of the derivative. So if I have, x cubed, that would be my function. F prime, or the first derivative would be 3x squared. The second derivative would be now the derivative of that, or 6x. Does that make sense? Good. And what we can do is we can use that second derivative to tell me, oh, this is what's describing the concavity. When our second derivative is positive, it tells me that it's concave up. The derivative is increasing. In other words, it's looking at the slope of the derivative. I know that's kind of crazy, the slope of the slope. But if the slope is constantly overall increasing, okay, so we're finding the slope of the slope, we can see, oh, it's concave up. If the second derivative is negative, then it must be concave down. In other words, overall, the slopes are decreasing or becoming more negative. Then in that case, we can see that it must be concave down. The point of inflection is that point that I was describing to you, and I won't scare you again. It's the point at which those wheels are perfectly straight. It is that moment that you're turning from right to left and your wheels are perfectly straight. The point of inflection is when your second derivative equals 0. Let me say that again. It's when your second derivative equals 0. That is the spot. Now the point of inflection happens to also be, and I just want to make a note of this, it is where the slope, okay, is the greatest. It is the highest. Let me just show you just a graph just so you can follow this. If we were turning, you know, doing our lovely little winding road here. Here it's 0, and you're turning to the left, and you're about to turn to the right. Does that make sense? Or you're concave up, and you're about to become concave down. It's at that spot where those wheels are perfectly straight. Again, you know, turning to the left and then turning to the right. That pathway there, the moment where can you see that the slope is the steepest there in the same way as we're coming down this way? So we're concave down, right? And then we're going to turn to be concave up here. This section is more concave up, where this section is more concave down. At that point of inflection is where the slope of that line is the steepest. Good. Okay, so we're to refer to this graph for some questions here, for questions 11 through 14. And so I want to do just that, go through some questions with you. Okay, so as you notice, this was part of the packet, part of the homework, and it is in the packet, so hopefully you did just that. You have your packets with you, and you're hoping to do that. I'm actually going to do the homework with you here. So it says define all the points of horizontal tangency. I'm not going to go through every part of these. I'm going to actually leave some of this blank because I want you to come up with them. But I want you to just be able to notice this graph. When I look for all the points of horizontal tangency, I'm looking for all the spots that have a minimum or a maximum. Make sense? And even at times might be a relative minimum or maximum. And again, we could have a point of horizontal tangency nestled in the middle. So let me just give you an example here. We can see that we have a horizontal tangency here. I have a horizontal tangency here, and I have a horizontal tangent. These aren't the only ones, but those are just 3 of the points of horizontal tangency that you should be able to see where you're looking at that. If you're looking at 12 and it says to find the limit as x approaches infinity, in other words, that's the last thing your graph is doing. I want you to look all the way to the right, and what's the last thing your graph is doing. And then secondly, in part B, what is it doing as it approaches negative infinity? And then in 13, finding minimum values, I want you to notice the intervals that are being presented to you as from -4 to -2 or whatever. I want you to actually look at those intervals so that you can examine what are the minimums just within that interval. And then again in 14, now I want you to be able to answer as it's increasing or decreasing. Pay attention to whether it says F or F prime as you look at that. All right, let's do some examples that kind of go along with these. Determine whether the following are positive, negative, or 0. When it says f of 3, what that basically is saying to you is the value of f of 3. So here's where 3 is. So I'm going to look here on the graph. Is that positive, is it negative, or is it 0? Well, the value of that is positive. The slope, what is the slope at that point? Positive, good. Now, here's the thing. Remember, first derivative, we could see it's going up. That's kind of obvious. The second derivative is talking more about concavity. So is it open up or is it open down? And if you look, here's the curve. It is open up. That would be positive. F of -1. Now let's look at that. Okay, here's where -1 is. -1, at least it looks according to this graph like it actually is negative. So that value is -1. I feel like that's supposed to be on that little spot here. So I'm going to just use it as if it's at that maximum spot. So apologize if this is slightly off, but we're going to pretend that that's where -1 is. We can tell the value of f of -1 is negative. That's easy. The slope of this spot I'm just going to say is 0 because I'm, again, assuming that it's at that spot. Apologize for my drawing. Now, what about the second derivative? It's where it's concave down, so it would be negative. Okay? How about of negative 2? Negative 2 falls here. I'm going to erase this just so that we can see a little bit better. So now we're at negative 2, and we're going to be more here. Okay? Its value is negative. Its slope is negative. And its concavity is concave down, so it too would be negative. Now, how does that look as we're graphing something? When you're graphing something, it just adds another dimension to it. The first step doesn't change. We always start with plus or minus infinity. And so that is our first step. So I'm going to put plus or minus infinity in there. So infinity cubed is infinity, and negative infinity cubed is negative infinity. Second step. What was the second step whenever we're sketching any curve? Points of horizontal tangency. Good. So what does that mean to do? That means we got to take the derivative and we got to set it equal to 0. So we're going to basically solve this and find where those spots are. So I get plus or minus 1. You'll notice that I didn't forget the plus or minus when we take that square root. Now, a third step that we're adding to this now, okay? The third step is we're going to find the point or points of inflection. And these are all very critical pieces that we need to make sure that we have. So the points of inflection, this is when your second derivative equals 0. So I'm going to take my derivative, 3x squared minus 3, I'm going to do its derivative, which would be 6x, and I'm going to set that equal to 0. And so I quickly find that that's at 0. And so now there are 3 different points that I've got to find, but that point of horizontal tangency is just as important as these points of inflection. We've got to make sure all of those are done. All right, so let's just do the points of inflection. I got to look at that equation again, sorry. So moving that back up. So 0 cubed minus 0 plus 1. So that's the point of inflection. For my point of horizontal tangency, for those, I need to plug in 1. So I'd have 1 cubed minus 3 plus 1. So that's negative 2 plus 1, or negative 1. And then as I put negative 1 in there, I get negative 1 plus 3. So that would be 2 plus 1, which is 3. All right, now we're going to do that graph. So to do the graph, what we can't get tripped up by is that point of inflection. I almost would like you to kind of separate that from everything, just because it does tend to trip people up and when you draw the dots, and you'll see what I'm talking about. So you have 1, negative 1. People just almost make it another spot where they put a coming in at 0, and you got to be careful. And then negative 1, 3. So basically, here's my 2 points that I'm working with, and I'm going to connect them coming in at 0 and kind of going up like this. And then as I go to infinity, I'm going up, and negative infinity, I go down. You'll notice that this is where my point of inflection was supposed to be, and it should be at 0, 1. So it is a little tricky. I'm going to redraw that actually, just so that I don't mess that up. But because I'm not doing an exact graph, it kind of messed up on me. I'm going to be a little more particular. Negative 3, and then I'm going to do negative 1, 1. Okay, and oh, sorry, that's where my problem is. Oh my goodness. I'm doing the wrong way. Probably if we were in class, you'd have picked that up, huh? 1, negative 1, and negative 1, 3. So it's going to come in, and it's going to cross here at 1. That's that point of inflection that we wanted. And we're going to go up, and we're going to go down. And so that point of inflection at 0, 1 would be the part that we would need to make sure is noted. And so there you go. There's your graph. Not much different than what you've done. We just now have another piece of information, that point at which it changes from concave down to concave up. So if I was to ask, when is this concave down, you would say that it would go from negative infinity to 0. And it would stop at 0. And then from 0 to positive infinity would be concave up. Okay? That point is that breaking spot. So there you go. Okay, excellent. And that concludes the video for now. Remember to complete all the way up through 14 as your homework.